In front of us we see a couple of equations that are not quadratic equations. X squared is not the highest exponent in each one of them, but we are going to be able to use some of our quadratic techniques to solve. And so, for example, on the first one, we see that we've got x to the fourth is the highest exponent, x to the second is next, and then there's no x in this third piece. So normally when we see that higher exponent of x, we're going to try to undistribute something. But in this case we can't because there's no x attached to that 27. We also don't want to use that factoring by grouping approach here where we undistribute from only a part of the problem. It's not really going to lead us anywhere if we try to pursue that tactic. That really only works in those special circumstances where we can go through that full factoring by grouping process. So instead what we're going to do is we're going to reverse FOIL this problem as if it was a quadratic. We're going to factor it into two sets of parentheses, into two binomials. And the reason we know that we can do that is because the exponent on the highest exponent in the problem, the exponent on that lead piece, 4, is twice as big as the exponent we see in the second piece, 2. If this was x to the sixth and then x to the third in the middle, this would also be a circumstance where we would be able to factor using our regular quadratic techniques, our reverse FOIL. And so instead of having x as the first piece in each of the sets of parentheses, I'm going to have x squared. And then I'm using my regular reverse FOIL process where I'm going to look to see what multiplies to make negative 27 but adds to make negative 6. Well, if I'm multiplying to make a negative, I need one of each. Beyond that then, two numbers that multiply to make 27 and add to make 6, or have a difference of 6, are going to be negative 9 and positive 3. So 3 times negative 9 gives us that negative 27. If I was to reverse FOIL, x squared times x squared would give me x to the fourth, and then these outer and inner terms would give me the x squareds that I need in the middle there. So we can see that we can factor expressions that have higher order exponents. Again, as long as the first exponent is twice as big as the second. And so from here, we can factor one more time. I can say x squared plus 3, times x plus 3 times x minus 3. So I can use the difference of squares in that second set of parentheses. Can't really do anything with that left-hand set of parentheses. So at this point we can go ahead and set these all equal to 0. So I've got x squared plus 3 equals 0. I've got x plus 3 equals 0. And then I have x minus 3 equals 0. From there then, I can solve these two easier equations on the right very quickly. Hopefully we see that we get negative 3 and positive 3 as our two answers. Over on the left, since that's not factorable, we're going to isolate the x squared to equal negative 3. Now we can take the square root of both sides. So we've got x equals, now of course we need a plus or minus, and then we've got this root negative 3, so I'm going to separate out the root negative 1 times the root 3. That root negative 1 becomes an I, and so we've got x equals plus or minus I times root 3 to go along with the plus or minus 3 that we have over here. So we can see that we end up with 4 answers, just like we would expect with the highest exponent being 4. We just end up with 2 imaginary and 2 real. For the second one, as gruesome as it seems to see those fractional exponents, the same thing is going to apply. If we look, we've got x to the 2/3 as our exponent on the first piece, x to the 1/3 in the middle, no x in the last term. So we have that rule that we've followed in the last one that indicates that this one's going to be factorable of the second exponent being half the size of the lead exponent. So I'm going to move to my two sets of parentheses. I can see that I have a coefficient of 5, so I'm going to have a 5 and a 1 as my two coefficients in the two sets of parentheses. And then it's like it was on this one, when it was x to the fourth was the highest exponent, x squared was the piece we put into each of the sets of parentheses, which matched with what was in the middle. Same thing here. X to the 2/3, half of that would be x to the 1/3, which is what we see in the middle here. So I'm going to factor this into 5
x to the 1/3. Let's try that again. So 5x to the 1/3, and then just 1x to the 1/3, or just x to the 1/3. Then I have to decide if I need two positives, two negatives, or one of each. So since we're multiplying to make a positive, but adding to make this negative in the middle, we're going to need two negatives. And we've run into a piece of good fortune here with the 1 only being able to break up as 1 and 1. And so indeed we can see that if we were to refoil this, we'd get back to the original. 5x to the 1/3 times 1x to the 1/3 would be 5x to the 2/3, since we would add those exponents together by multiplying like bases. And then we would end up with a negative 6x to the 1/3 in the middle, and that positive 1 at the back end. So now I'm just going to take each of these and write them as their own equation set equal to 0. But I'm now at this point going to change this x to the 1/3 into radical form. And so hopefully we recall from our previous study that instead of, we can write this as a cube root, because whatever number is in the denominator is going to be the root. Whatever number is in the numerator of the exponent is going to be the power of the variable underneath the root. So I've got 5 cube root of x minus 1 equals 0, and then I have just 1 cube root of x, or just the cube root of x minus 1 equals 0. And so now I just need to solve these two mini equations. So I'm going to add 1 to both sides here. So I've got 5 times the cube root of x equals 1. I'm then going to divide both sides by 5. I like to do everything I can to isolate that cube root or square root or whatever it is before squaring or cubing both sides. So now I've got the cube root of x equals 1/5. And so now, indeed, I just have to cube both sides. And so I get x equals, and then 1/5 times 1/5 times 1/5. I'm going to get 1 over 125, 1/25. And then for the second part of the problem, same idea. I'm going to isolate that cube root before cubing both sides. So I've got the cube root of x equals 1. When I cube both sides, I get x equals just 1. And so I've got my two answers to this problem. So on this one, we couldn't look at the exponent and necessarily know how many solutions we were going to have quite as easily, but the clue was in there. If we just ignore the denominators, as long as those are the same, then we can see that we have 2 as the highest numerator exponent, which indicates that we're going to end up with 2 answers.